Hi, I'm Kian. In this video, I'm back with another video on partial differential equations. And here we have a system of partial differential equation. So we have the second partial derivative with respect to x of a function u, which is a two-variable function, is equal to 0. And similarly, um, the derivative firstly with respect to y and then with respect to x is also 0. So how I'm going to solve it, I'm going to first tackle the second equation, this one, and try to solve it. So here, we see that we have to, so we have a function that first we take the function, the derivative with respect to y, and then we take the derivative with respect to x, and we end up with 0. So first we can actually integrate this function with respect to y. So if we do that, the dy goes, so we get u of x. This means that this is a partial derivative with respect to x. And this becomes, since this is 0, integrating 0, we get this c. But here, since we are working with multivariable function, this c here, since we're working in terms of x, this just becomes a function of x, so I can call it g of x. And it makes sense because if we take the derivative with respect to y of g of x, it becomes 0. So this kind of tackles the same as a constant, so it doesn't differ from a constant. Now this becomes the partial derivative with respect to x of u is equal to g of x. So if we integrate this, what we get is here that u is equal to the integral of g of x. We can call it capital G of x, and then plus c. But again, we call that c to be a function of the opposite variable, or here we say as h of y, a function of y. And if we actually want to check if our answer is correct, first if we differentiate the function u with respect to y, this part goes out because any variable other than y is considered a constant, and this h of y becomes h prime of y. Now we have a function in terms of y, and if we take the derivative with respect to x, that also is a constant, so it becomes 0. Now, we need to function in terms of kind of u in terms of x and y that also makes this equation true. So this is our general solution, capital G of x plus h of y. But if we plug this into here, this is not true for all values of this function. So we have to kind of generalize it more and find a value for the function that makes the equation true. So if we consider this to be the general solution of this system, then I'm going to use this form for solving the second equation. So if you use this, if you take the first derivative with respect to x, what we get is the derivative of g of x, capital G of x, or we can call it just g prime of x. So I can call u x to be, I can call those with small g, it doesn't really matter. I'm just going to call it g prime of x. And then when we do it a second time, we see that uxx, or the second partial derivative with respect to x, would be g. This is also g. Oops, I'm sorry, I'm going to erase this. So this is a g, and then this becomes a g prime of x. And then this is equal to 0. So what we have is actually a function in terms of x that its second derivative is equal to 0. So this is a pretty basic ordinary differential equation, because if you think about it just normally, what function would its second derivative be 0? So technically, if we take the integral of this, this becomes a constant c, so here g of x, g prime of x would be c, and we take the integral a second time, g of x, or the original function, would be cx plus a, or a linear function. So we see that we can write g of x as a linear function. I'm going to write it in the actual mx plus b form, so mx plus b. And you're basically done, because you have the function for g of x, and it actually doesn't matter what h of y is. And the reason is, let me write our final solution. So we have u is equal to when you use red again. We have a function of y. We can call it anything. I'm going to call it h of y plus mx and then plus b. This is the most general solution. So here I'm going to call this actually capital G of x. So this is the G of x, the function with respect to x part, and here is the function with respect to y part. And the reason I told you the hy doesn't matter is that in this first equation, when we take a derivative with respect to x, the h of y cancels out. So it doesn't matter if it's y squared, if it's sine of y, anything it is, it cancels out. Similar to this one, if we take the derivative first with respect to y, we get h prime of y. But then we're taking a derivative with respect to x. So again, it doesn't matter. If this is sine of y, this becomes cosine of y. But again, taking a derivative with respect to x, it becomes 0. So actually, h of y can be anything, and we can find it given the initial conditions that the partial differential equation gives us. But this is the general solution that satisfies both of these equations. Thank you for watching, and goodbye.